Okay, so yeah, go ahead and keep copying this down, these notes. Anybody need more time or no? All right. Are we also waiting on? Do you guys know if Greta? Let's see. Um, Gabby. Gabby's sick. Okay. Okay. Oh, during the day. I mean, probably. Thank you. All right. Thanks for letting me know. Anywhere from Elena or no? No one knows the whereabouts of Elena Thompson. Joseph comes in a little bit later too. Okay. You guys have any questions? What I wrote there, just let me know. I'll clarify what I wrote. Okay, I'm gonna unfreeze the screen. Give you guys a few more seconds. It's still the same thing. Okay, so we're gonna pause for 1 second. Whoops, sorry. I just wanted to show you for last week. I do apologize. It took a while to do this, but 5.2, I finally just posted up the videos for 5.2, which was the section I intended to go over last week. So they're up now in total. The second video, I do kind of fumble around a little bit because like I just kind of do it like what I call organically, but you can kind of call it like not as prepared as I should have been. So you'll hear me fumbling around stuff. So there's a lot of parts where you can kind of fast forward, but altogether, I would say this video is still about like 36 minutes or so. Okay. You can kind of tell I kind of fumbled around because the first part here, I didn't mean it to be two parts. The first part cut off because like I think as I was grabbing something, I knocked like the USB cord and like it just stopped recording. So that's kind of why it's in two parts there, right? But otherwise, all the week 1 stuff is finally now up. So if you haven't done 5.2 yet, please go over these videos, kind of take some notes and figure out what's going on with 5.2 if you don't know what's going on. Today, we're going to skip ahead and go to 5.3, okay? Let's see. And also, I have these videos here. This is from last year, basically. You don't have to watch these, but we already kind of went over it in class for about an hour, 7.3. And these are pretty much like very similar videos. I think, Sarah, you might have watched it ahead of time, actually, too. And then you'll kind of see as I get along during the year, I kind of wised up last year to start recording my lectures. So I'm playing catch up, if you understand what I'm saying. So like by month 6 or 7 is where I started to upload like the actual in-class lectures because I used to only do it for like people that were sick, but then I just figured why don't I just upload it for everybody. So hopefully when we get to that place, we can do other stuff in class, or maybe we can just keep, I don't know, we'll talk more about that during the year. And then next week will be your exam. Okay, my intention today is to go through 5.3 in class at least. And then I really want to get to 5.4, but of course, if I can't do it, I have to post it up sooner than I did this last video, 5.2. That was really bad. That was really bad of me to upload it so late. So, oh, and I have some backup too. So I guess I recorded this last year, but let's see if I was as good at explaining it last year or if I'm better at it this year. Okay. All right. So you just wrote some directions for finding local extrema. When I ask for local extrema, do you guys know what I'm talking about though on a graph? Like what is the local extreme point? Does anybody know what a local extreme point is?
It's like the point that's higher than the point around it. So like an extreme is like the top point. So if you had like a or very bottom. So if you had like a parabola, that extreme would be on here. But if it was like cubed, it would be like this, and this would be the.
So yeah, so on a graph, your extreme points are the highest and lowest points locally. So we know them as local minimums or maximums. And basically, I'm giving you skills right now or today to essentially solve for these without having to look at a graph. Okay. If you don't have a graphing tool, can you actually determine it by just algebraically working out some numbers? And the answer is yes, you can. So these are the directions. You can kind of follow along, but first you kind of find the derivative of your function. You find the zeros. Hopefully that sounds kind of familiar with finding your roots or your zeros. Then you see if the slopes around there are increasing or decreasing, and then that way you can determine if you have a minimum or maximum. What is that going to look like? So let's go ahead and start with one example. You're going to have f of x is equal to x cubed minus 12x minus 5. And then it'll ask you, like, questions like this will kind of prompt you to use the first derivative test. So they'll actually want you to explicitly do it. Use the first derivative test to find any extreme values. To find any extreme values. I'm going to write this on a separate sheet of paper here. All right, so I'm going to kind of cheat a little bit. I'll kind of knock this over to the... Whoa, that's not what I intended here. All right, can you still see that? I'll zoom in a little bit so you guys can still see, hopefully, as I'm writing this. Okay. Give that a little bit of clarity. And then I'm going to... come on. All right. I'm actually going to graph this to see what it's going to look like, just so we can get a sneak peek at what we're dealing with here. Okay, so I'm going to go to desmos.com. I'm going to graph this too. And it says use the first derivative test to find any extreme values for this function here. I'm actually going to graph this function and then see where are my extreme values up and down, right? But we're going to do work and pretend as if you don't have a graphing calculator, okay? So we're going to go back to like the Stone Age. Oh, not that far back because we weren't that good at calculus at that point yet, right? It wasn't really calculus yet. But who knows? Yeah. There's a lot of history in math that we aren't completely aware of. Okay, so we have x to the third power minus 12x. 12x minus 5. Can anybody think of what this shape's going to look like before I complete it? Any ideas what the shape might look like? No? Look, it's going to look like a cubic function. Yeah, that's absolutely correct. Yep. And how would you describe? Oh, sorry. Okay, so you can kind of see that there's like a local maximum there, and a local minimum at these 2 points, right? The real big key that I want to ask you, though, is if we had to find the slope at these two minimum maximum points, what would the slope be of these at these 2 points? Yeah, it'd be 0, right? So that's why the first step, basically, that I told you to do is find the zeros. So the first step I asked you to do is find the derivative of this function, and then set it equal to 0, and then find out where the slopes are literally equal to 0. Does that make sense? Because then you know that you have some kind of extreme point. So let's go ahead and do that. So step one will be to find the derivative. So it'll be f prime of x, and that would just be 3x squared minus 12. Not too shabby, not too bad, right? Not too shabby, right? Step 2, we would set this equal to 0. And then we would solve for 0. So we would just add 12 to both sides. And we have 12 is equal to 3x squared. Divide both sides by 3. You have 4 is equal to x squared. And then to get rid of the square root sign, or I'm sorry, to get rid of the squared exponent, we would take the square root of both sides of the equation. So you'd have 2 is equal to x. Is there any component that I'm missing to my answer to make this a more accurate answer?
It could also be negative.
Okay, so this infers that this is positive 2. Might it also be negative 2 as well? Yeah, plus or minus 2, right? And to that, we remember this is a cubic function, so it kind of makes like a weird N shape or something to that effect, right? So you should have 2 extreme points of minimum or maximum, right? So that kind of makes sense. That's where they may occur, okay? One other thing too, this is what we call a critical point. These are critical points. This is where your slopes are equal to 0, basically, okay? At these x coordinates, the slope is going to be flat there, okay? So these are your critical points. But look back on step number 2 really quick. Read to yourself step number 2. What does it also ask for besides critical points, though? It asks for another type of point as well for you to solve. Endpoints. But it's only where it's applicable. You will find endpoints according to the question. So in this case here, if I were to ask you to find the endpoints of this function, could you find an endpoint at each end of this function? Yes or no? Could you find the endpoints? Yeah, it's a subtle kind of like, no, I don't think so. Okay, but yeah, be really assured of yourself. There's definitely no way I can find the endpoints that goes on for infinity. Okay, so that step where it says find the endpoints, it only applies to certain questions. And hopefully I'll go through some problems where it's a little subtle, but you have to find the endpoints. Okay, but in this case you can't. It just goes on infinitely both ways. All right. Raise your hand if you've already done this section, by the way. Okay, this is not to, like, oh, great job, but I'm just kind of hoping that this isn't redundant information for all of you guys, okay? Okay, so step 3 is where you make a really odd looking chart. It's a number line. It's essentially a number line, which is all the x values. Like imagine your x-axis without the y-axis, without its awesome partner, right? Let's look at -2 and 2. Makes sense that I put in that order, right? Lower numbers go first, and as you go to the right, they become higher. We're only looking at our critical points. Actually, let's replace this x with f prime, just to let us know this is what we call a first derivative test. If there's a first derivative test, what do you think there is also existent in this section? Second derivative test. Okay, so the first derivative test, though, I'm going to show you how to do it actually before I talk more. Right. So step number 3. See if the slope. Oh, sorry. No, I'm not even on it. I'm sorry. Step number 3. See if the slopes and derivatives around your endpoints and critical points are increasing or decreasing. Why would this be of help for us? I don't know. Well, now this is hard to see. Let me see if I can annotate here. Can I annotate? Okay. I can't do this. I'm horrible at this, okay? All right. So I try my best to make a tangent line. That's not a tangent line, because why is that not a tangent line? It's not even touching the line, but
It's not even really a straight line.
It's not even really a straight line. All right, good. Cut me a break, guys. Cut me some slack, okay? But that's the slope at maybe this point here, right? And then here is another slope. Sorry, I'm not doing great here. And then here is another slope. And then finally, here is another slope here at this point. It's not perfect, okay? I tried my best, but I'm not very artistic here. But what do you notice about the slopes? in terms of their value? Is it increasing or decreasing as I approach from the left-hand side of this?
Well, it's getting closer.
It's getting closer and closer to 0, so what does that tell you? Is it decreasing or is it increasing, the slope value? So again, we start really steep. Give me a value of that slope, a really, really steep slope. Give me an arbitrary value, a value that you made up. Joseph, give me a number.
10.
10. If this one is not as steep, okay, what would you give that value then? Joseph again.
7.
7. How about here?
5.
5. And then finally. Okay, so what do we see the slope values doing? They're decreasing, right? And then, how about if we go to the other side? Okay. Okay, so what do you guys notice here? Wait, give me 1 second. I gotta make sure. Hello, Aurora, Miss Aurora. I just gotta make sure this works out. Is that what I wanted to do? Oh, you know what? Maybe. Did I get this wrong? Is it negative or is it negative or positive or is it increasing? Okay. Shoot. Give me 1 second, guys. Okay. Talk amongst yourselves really quick. I just got to make sure my information is correct because this doesn't seem correct. Okay, I think I got something wrong here, guys. I am so sorry. Here, let's go back really quick. Let's change our notes. So I do apologize. Shoot, yeah, I just had an epiphany here that maybe my notes were incorrect here. So here, go back in here in step 3 and then alter this really quick. So on step 3, it should say are either positive, comma, negative. This is huge. This is actually, yeah, this is actually really, really big. I do apologize. So, but it's good that I caught this now, or else we would be kind of going off the wrong information here. Okay, so it's not whether it's increasing or decreasing. I do apologize. Just simply tell me the sign of the slope. Is this a positive slope or negative? Positive. And then on the right-hand side, what is it? Okay, so as you can see, if you have a positive slope approaching the extreme point, and you have negative slopes on the other side, what type of extreme point do we have? It's a maximum, okay? So I super apologize for that, okay? But here, what you would do is you would actually plug in like, let's say that you didn't have that graph to help you. You would plug in any point that you want, like to the left of -2, and you'd plug it into this formula here, this equation that you created, this derivative. So here we saw visually that it was positive, and then the right hand side was negative. If that happens, this is a local max. So this is essentially step 4, is identifying what you have. Okay. But as I said, if you didn't have the graph, and I told you to do this by hand, okay, you would just plug in a number to the left or a number to the right into 3x squared minus 12. Okay. And then let me let's see, positive. I gotta fix that on my notes. Negative. Okay, and let's check this one. If you have negative slopes, then you approach this this critical value, which should have a slope of 0. And we saw on the graph visually, what was the extreme point at x equals 2? Did anybody recall? At x equals 2? What point would we call that? What type of extreme point is that at x equals 2? Yeah, it's a minimum, right? So as you can see here, the slopes here are negative from the left-hand side. And the right-hand side, what would you consider those slopes now? Positive, right? So here, you would say it's positive. So if you have a critical point that is sandwiched between a negative on the left-hand side, negative slopes on the left-hand side, and then it becomes positive slopes on the right-hand side, then you have what we call a local minimum. Okay, it's not too bad. I believe that's it. Yeah, that's all I ask you for. Hypothetically, again, if we didn't have a graph, someone pick a point that's greater than 2. Anyway. What, 6? 5? 5? 5. Okay, so we'll just say, I just test a point here. So I'll just say 5. Okay, x equals 5. And then you can do the test like this. You do f prime of 5. And then you just do 3 times 5 squared minus 12. You can actually just stop right there if you can recognize that this is a much bigger number than 12. Or you can just keep going on. That would be 3 times 25, which is 75 minus 12. I did that in my head. So let me see if I did that right. 5 times. Yep, that's 75 minus 12. You could just stop right there, but you can keep going in case you just have to know what it is. That'd be, I think, about 63. Did I get that right? Yeah, 63. And you just ask yourself, is that a positive or negative number? That looks like a pretty positive number, okay? So at that point, you can determine that all the numbers bigger than 3 are going to give me positive slopes at that point. Does that make sense? Because they're bigger, yeah. And then vice versa for over here, there's a certain limit that like up from the range of -2 to 2, all these numbers should give me a negative slope, okay? All right, let me give you an example for you to try, and then let's see how you guys do, all right? So here's a challenge, no graphs, okay? So you can't graph, you cannot graph, okay? Do the same thing for this guy here. F of x is equal to x squared minus 3 times e to the x. This is going to be pretty tough. Please find a space on the whiteboard to find a whiteboard to work on this, okay? Let me go ahead and do that. And Sean, can you get one of the lights for me? Just one for now, so that way everyone can see the problem. Okay, so you guys can still make up the problem for now. Good luck, okay? I'm going to give you guys about like 10 minutes or so to figure this out, okay? Phew, that's not great. What the heck? I need to fix that. Positive. Oh my gosh.
No, that's
Oh, yeah. Oh, yeah, that's right. It's good.
Dear me. Yes.
Is that x squared minus 3, not minus 3 in the x?
Hold on, Ashlyn. I know. Ashlyn. Hold on. No, yeah, it's x squared minus 3. good that you asked because I'm always prone to many mistakes. So just always be on your sharpest with me. Okay. Or positive and negative. Okay, very good. So this is going to use the product rule because you have two differentiable sort of expressions here written that are being multiplied to each other. So you will have to use the product rule. Yeah. That u and b. So you take the derivative of the u times b. I like your. Okay. Yeah. What is this? The point of it. The hard part, I think, would be finding out the roots. Or maybe not. That's correct. There you go. It's hard to kind of read. Very good. Very good. Anybody need help? Walk around it. You need help. Oh, okay.
What did you say?
5 more minutes.
Equal to 0. X plus 2x.
Do what's called a concavity test. Oh, freeze frame this for you guys. Where's my pen?
Where is my pen?
Are you trying to find the root for e to the x? Is there a root for that? Yeah, no matter what you try, there's no value of x that would make that 0 when it's an exponent. You only have 2 roots. That's fine. Okay. Yeah, that's perfectly fine. Yeah. So guys, don't be scared if you get to the part where you have e to the x times that polynomial, x squared minus 3x, or I'm not really sure, plus 2, or x minus 3 plus. E to the x, there is no x value that makes that 0. Does that make sense? Okay. So you should only have 2 roots.
That's why you just take it out.
I mean, keep it there.
And
But
stop.
it's just not, you're not going to make that equal to 0. Okay. But we can make it equal to 0. So You just gotta split that out. 2 by unfold. Factor it out. F double prime. Find the zeros. Double prime or inflection points. Inflection points. And then terms. All right, guys, if you guys are finished, go ahead and have a seat. I will go through this with you in just a second. Of a function as a tangent line and where okay, I'm gonna go ahead and post up my key. It's gonna look a little odd. Okay, so Ms. Risa, can you get the light turned, please? Thank you. Do you guys hear it's supposed to rain today? Yeah. Okay. Anybody notice that it was fairly bright, just like not even half an hour ago, and now it's like insanely gloomy? Okay, so be very careful if you drove. Okay, so you guys drove here. Okay, so this one I know. Don't look at my weird number line, but I did use the product rule, which is U and V. You set a U and a V, like two differentiable parts, like that, two separate differentiable parts. I saw x squared minus 3 is differentiable, and then e to the x is also differentiable, and they're being multiplied. So then you do what is it? V prime times U plus U prime times V. You should have gotten to this point, x squared plus 2x minus 3 times e to the x. And then you could have factored this out into two binomials, x plus 3 and x minus 1. And I did mention that e to the x, as much as that you try to set that equal to 0, you will not find a x value that will give you 0, okay? And that's perfectly fine. However, you can set these equal to 0 and actually get two different roots. X equals -3 and x equals 1. So we could go to Desmos, or I kind of gave you, yep, what you the natural logarithm you said. So at this point here, my number line is actually kind of hidden. It's still there. It's this green line right here. There are the two critical values, -3 and 1. And then I found that I tested some points around here to the left of this critical point, and they were positive. Did everybody get that? Yes. And then I tested some derivative points.
I feel we need to test it one because if like there's if it's positive, then if it crosses the 0 line on the derivative, then it must be negative, and then crosses the 0 line again, it would be positive.
Possibly.
Alternates.
Yeah, that's true. It's true. But you're gonna see that. Don't always assume that though. That it might. In this case, in the first derivative test, it will. You're gonna see in the second derivative test there are instances where when you cross Well, that's different. It's not positive and negative, but let me get there, okay? But don't always assume. Always just test. Always just test points just to be sure, and just show some work too. So I know it's kind of weird here, but if you look kind of in the background in black, you don't have to do this. That's the actual function and what it looks like. Okay, so in your book, sometimes on top of their number line, they might actually start drawing to get real fancy. They'll actually draw what the actual function looks like, so you can actually see for yourself that from here, from infinity, negative infinity to -3, all the function is slightly increasing. The slope's always increasing. Here it hits a flat spot right here where the slope is equal to 0, and then all the points from -3 to 1 are decreasing in slope. Okay, or you could just test a point anywhere from -3 to 1, and you should get a negative slope. All right, and then anything to the right of 1 should give you a positive slope. Okay, again, here's what the function looks like. So you can clearly see that this is a local maximum, and then this is a local minimum. Okay. Oh, and don't worry about my weird kind of talks here, right? Just that's at least a minimum, right? We're going to move on to the second derivative test. Go ahead and take a few minutes to write this down, okay? It's almost exactly like the first derivative test, except guess what? You go one step further with taking the second derivative. The only difference is your critical values are no longer called critical values. It's still the same concept. You find out where your roots are, okay? Your zeros in step 2 for f double prime. For 1, they're called inflection points. And then step 3, the only difference is this is where you don't look for positive, negative. You do actually look for whether it's increasing or decreasing. Okay? So I do apologize. It's kind of good, though. I guess you kind of got a sneak peek unintentionally from the first derivative test. What we're kind of looking for when we're looking for numbers around the zeros. Okay? You don't know what I'm talking about, so okay. And then write this down too. What is a point of inflection? It's a point where the graph of a function has a tangent line. Basically where, sorry, that says concavity. I don't know how it got that. It looks like concavity. Okay, so that looks weird. So let's concavity. Where concavity? Does anybody know what concavity is? How would you describe concavity? It's an odd concept.
Like a spoon is like concave.
Concave. So could you do with your hand? Show me with your hand, Stephanie, what concave up would look like. It'd be like a cup up. Okay. If you can imagine your graph cupping upwards, it looks like it's kind of pointing the cup upwards. And if you can imagine a graph where it curves in such a way where it sorts to cup facing downwards as it kind of cups up, but it faces down. Okay, that's concave down. Okay, but it's hard to detect because you might argue it's all about relativity in your perspective. Okay, but we need some sort of common understanding about what is concave up and what is concave down, and this test kind of gives you a uniform way of thinking, right? Because what one person's visually what they perceive to be concave up might look like concave down to them for some reason. Some of these functions look really weird, right? So this is a nice uniform way of kind of having common ground, common meaning about what is concave up and concave down. So this is from your book. Oh, did everybody write that, or do you need a little bit more time? Here, I'll give you a little bit more time. Oh man, I'm messing this up. Okay. I'll freeze that for a second, and I'm going to load up the my image that I want to show you. Oh, there we are. Okay, everybody got that? Sorry. Okay. Let's take a look at concavity and what this means. This is in your book. This is on page 213. All right. So this is kind of a mind up a little bit, right? So at this point here, you can kind of see the graph cupping downwards. Can you not? Yeah. And then wherever it switches, it starts to kind of cup upwards, is where you call it concave up. But let's take a look at the slopes and how the slopes are changing. Okay. So you see here, so now this is where we kind of get into what I was trying to explain earlier, but I wrongly explained, okay, for the wrong test. This is the test we're going to do this with. I'm trying to get like I think this might work. Okay. Let's say I'm trying to get a tangent or like a slope that is tangent to this point right here, right? Like this point right here, and I'm going to try to make a slope that is tangent to that, right? That's pretty big. So Joseph, now please give me an arbitrary slope value for this slope. This yellow sliver represents that slope of this point right here.
About 6.
How about 6? Okay. And over here, it's kind of slanting a little bit more. Come on. Okay. Right here. How about now in comparison to what it was? It was here. Okay. Sorry. This is not a great visual example. I'm trying my best here. And then here, it's getting a little bit more flat. How would you describe that now, Joseph, if you had to give it? 4. Okay. How about now? Sorry. How about here? Can you guys see that? I don't know if I'm doing this right.
Like 2.
Okay. And then eventually, when we get to the point of inflection, or this critical point, what would you describe that now as? 0. Okay. Thank you so much. That was not easy to do with this flimsy little thing here. Okay. But you do notice that as the slope decreases, it's changing now, right? It's decreasing. Then you get concavity going down. Okay. You can find that in anything that has a concavity going down on any of those graphs. Okay. But notice what Joseph kind of says, that right here is a flat spot, or I even said it's a flat spot, right? I kind of gave it away. That's what we call the point of inflection, where if you notice, I'm not going to try to do that post-it note again, but just follow the lines here, right? It goes from, okay, nice steady kind of slope here from this line, if you can kind of see this lower line. And then as we get closer and closer to what I like if we get more and more points going upwards here, we notice the slopes kind of shift going more vertical, giving me higher slopes, right? That is an increase of slopes. And notice I'm saying the slopes are changing. Slope in itself is already a change, right? What's the word that we use for a slope at one point in calculus? It starts with a D. We've been saying it this whole time. Derivative, right? But if I'm looking at how the derivative changes, how the change of a change is occurring, another way of saying that is the second derivative. Does that make sense? Okay. So that's why it's called a second derivative test. We're looking at how the derivative changes, which is the derivative of the derivative. So that's what we're looking at here. And this actually doesn't always happen. It doesn't always go from, so Stephanie, what you said before, if you guys kind of got what she said, it was actually really inquisitive. She said, if I find 1 point and I test 1 point and I find out the sign, I can kind of find out that as long as I test out the sign from the first, from the far left, I think, I know exactly how the signs are going to change going from left to right. If I get a negative slope here, I think I'm getting ahead of myself. I'm sorry. Okay, so I'm going to stop, okay? I don't want to further confuse you guys. Okay. All right, so I'm just letting you know, though, that's not, there are instances where your y or your slope doesn't go from decreasing to increasing. It may go from decreasing to decreasing. Let me see if I can create an example later about that. But that means you don't have anything. You don't have any concavity change. But let me see if I can kind of run into a problem where that occurs. Let's see. Concave up, concave up. Okay. Let's give you an example now. So, getting ahead of myself. Okay, so let's go through an example. What example do I have for you guys here? Here's your example. It will be, don't be scared, okay? You're used to seeing the f of x. Now we're going to change the notation to trick you intentionally. It's the x of t, okay? Don't be scared. X is just a function now. X of t. T is now the new independent variable. It's 2t cubed minus 14t squared plus 22t minus 5. Here's a condition. It explicitly says they want your condition to be greater or equal to 0. So, my lovely people, what is my first step to figuring this out?
Well, they didn't really ask what they wanted.
Oh, sorry. Let's see. Solve for. Actually, yeah. Before I do that, let's see. Tell me. You won't find this in the book. It won't ask you to tell me, but tell me the intervals for. Let's see. How would they word it? Yeah. The intervals for which the function. Tell me the intervals for which the function. Tell me the intervals for which the function is concave up and concave down. Concave up and concave down. So that's the directive right there. What's the first step? You take the derivative. That's great. That'd be x prime of t. And that's pretty easy. That'd be 6t to the second power minus 28t plus 22. But I'm looking for concavity. So what does that mean about what I just solved? If I'm asking for concavity, I'm not asking for the extreme points, the minimum, maximum. I'm going one step further. I'm asking you to determine that. Yeah, go ahead.
Yeah. We have to find the derivative of the derivative.
We have to find the derivative. Whoa, crazy moment of the derivative. Okay. Oh, earth shattering. Okay. It was to me because I didn't think that you could take a second derivative. In fact, I didn't want it. I didn't want you to be able to take the second derivative because that's just too much to comprehend for my mind in high school. It still is very tough on my mind now. Okay. But it's not that bad, is it? How hard was that going from one derivative to the next? Okay. Not that bad. In fact, doesn't it make step 2 a little bit easier now? in some ways. You got to find the zeros. Where is the slope of the function equal to 0, or the slope of the slope equal to 0? Basically, just set this equal to 0 and find me the zeros. Or set this equal to 0 and find me the roots, okay? So set this 0 equals 12t minus 28. You add 28 to both sides. You get 28 is equal to 12t. Divide both sides by 12. And you get t is equal to... Oh, thank you so much. You have saved me some time into flipping my page and thinking about what I wrote. Okay. Is there anything else I need to bring up? Yeah, that's it. Okay. All right, great. Okay, step 3 is you just draw a normal number line again. This time you might need to plug in more than just one value, though. Right? Or do you? I don't know. No, you don't. I don't know. Yeah. Okay. Someone pick a value that is less than 7 over 3.
0.
Picking a hard one, aren't we? Okay. So we'll pick 0. Or t is equal to 0. I'm so sorry. T is equal to 0. So technically this is in terms of t. Okay. T is equal to 0. And then we're going to do the x prime of 0. Okay. I know it's a little funky notation. We do 12 times 0 minus 28. I believe that's just negative 28. Okay. And let's try one more point. A point that's between 0 and 7 over 3. I'll give you a hint. Pick an easy one. Don't pick a complex one.
1.
Just one. Yeah. I like one. One's kind of nice. 7 over 3 is definitely a little bit bigger than 1, or quite a bit bigger than 1, right? So we're going to do x double prime of 1 is equal to 12 times 1 minus 28. And then we get, what is that? 12 minus 28. That's negative 16. What would you say is happening to the second derivative as we go from the left to 7 over 3? Yeah, it's increasing. So I'll say it's increasing. And how about the right-hand side? Pick a number that is bigger than 7 over 3.
3.
Okay. So 7 over 3, I think if you do that, that'd give me 2 and a third, or 2 and 1/3. So it has to be bigger than that. I'm just going to pick a whole number. So let's do x double prime of 3. That'd be 12 times 3 minus 28. That'd be 36 minus 28. I think that would just be 8. I guess you could pick another point, but I don't know if you need to. Let's do x double prime of, I'm just going to do 4. That'd be 12 times 4 minus 28. That'd be 20. Okay, so again, what do you notice about this? What is it? What do you guys notice about, I'm sorry, the second derivatives? Or, yeah, how the slope is changing. Wait, shoot, hold on. You guys might not be happy with me here, but shoot. Oh, guys, here. Sorry. Go back 1 second. You don't plug it into. I am so sorry. Here. Give me. Go back. You wrote this in pen. I am deeply sorry. Who wrote this in pen?
I did, but I don't care because I crossed things out like, it's time, and it's
All right.
nothing, and doodles everywhere.
I'm so sorry. You don't plug it into the. You don't plug it into the slope, the second derivative. You plug it into the first derivative. I apologize. I forget this is a. There's actually two ways you can do this, but I'll show you what is it? What is more, what is it? What aligns more with the concept that I've been talking about? So what you're supposed to do, I'm so sorry about this. You're supposed to plug it into the original slope and see how the slope, like how the value of the slope is increasing or decreasing. So I do apologize. So it's x prime of 0, not x double prime. So it will take a little bit more time. So x prime, what you're going to have to do is you're going to have to take the first derivative here. The first derivative, which is 6t squared minus 28t plus 22. So there's going to be quite a bit of work. I'm really sorry about that. That's
Not when it's 0.
so it's going to be 6 times 0 squared minus 28 times 0 plus 22. That's going to give me, what's up?
For 0 and 1, it's pretty easy, but like when you.
Yeah, once we get to the bigger numbers, I know. Yeah, it's kind of stinky. It's kind of stinky. I'm sorry about that. And then t over 1, or t is equal to 1. You're going to do x prime of 1. That's going to be 6 times 1 squared minus 28 times 1 plus 22. That'd be 6 minus 28 plus 22. Oh, whoa. Okay. And that will give me 0, right? So in this case, I'm sorry. So what is the slope doing now? What is the slope doing? Yeah, so it's decreasing. So my apologies, guys. Super apologetic here. Decreasing. And then over here, I suggest someone get out their calculator just to save some time right now. We're going to do x prime of 3. That's going to be 6 times 3 squared minus 28 times 3 plus 22. And then do the same for when t is equal to 4. So that'd be x prime of 4 is equal to 6 times 4 squared minus 28 times 4 plus 22. Can someone give me, if you did it in the calculator, what did you guys get for this here when you plugged in 3? Okay. Okay, so what is the change of the slopes here? Is it increasing or decreasing? So it's increasing. Okay. So now let's take a look at this actual function in Desmos to see what that would look like for concavity. So the original function is 2x. So again, I know it's a little bit weird because it's t. So it'd be a 2x cubed minus 14t, or x, sorry, squared plus 22x, I'm sorry, and minus 5. So the point of inflection, I believe it's 7 over 3, which I believe is 2.3333. Okay, so I'm going to try to talk. Yeah, I almost had it. Bam, okay. Oh, I didn't freeze it. Did I freeze it? Is it frozen? No? Okay, sorry about that. Okay, that's close enough. Is it frozen? Okay. Okay. So what do you notice about the concavity here?
Down.
It's down. Okay. And then how about now as the concavity changes? So this would be if you have a decreasing. Again, if you have a decreasing slopes, then you have concavity going down. Does that make sense? If you have it going, if you have it increasing, then you have concavity going up on the other side. Does that make sense? Okay. So here, what that would look like for your final answer. Sorry for all the confusion, guys. I'm really, really sorry about that. This is simply concave down. This is concave up. I would say there's one more strategy to this. If you don't want to do all that work, you know how I plugged it into the first derivative here, which is kind of weird because the last test, I didn't do that, right? The last test, if you remember, we actually, like, it was for the first derivative and I took the first derivative, right? Here, if you guys wanted to instead, it's a little confusing. Bear with me. If it makes sense to you, then you can use this technique instead, okay? Instead of testing to see if the first slopes, how they're changing, you can take you could take the second derivative, and if you get the second derivative, you could take just 1 point, okay? Like the second derivative being 12t minus 28. If you just take 1 point to the left of that and you plug it into this, you go by the sign. So if you get a negative number, then you get concave down. That's it. You don't have to compare between two of the first derivative tests. If you test it again and you use the second derivative and you plug in any number to the right of this, just one number, and it's positive, you get concave up. Okay? So there's two ways to do this. I like doing this way, even though it takes a little bit more work. It just makes more sense in my head. But if you'd rather just do something quick, you can also just plug it into the second derivative and go by the sign. Does that make sense? I'm going to give you the option to do either or because I'm going to give you a problem to do now. Okay? Here is your example problem that you're going to try here. And I guess this is going to be your ticket out the door before you leave here, because this is the last thing that we're going over today. It's going to be back to y. Y is equal to 4x cubed plus 21x squared plus 36x minus 20. I'm going to open up the floodgates. You may use your calculator as well, but more to check your answer. Find a space on the whiteboard. This is your last problem of the day, guys. You guys got about 10 minutes to finish this, okay? What's going on?
Hello. Can we do something that we did like 2 weeks ago?
You gotta wait till after class.
After class?
Yeah.
Okay, sorry.
Yeah, that's all right. Yeah.
Do they have it in class?
Yeah, but right now they're in the middle of like a
Yeah, okay. So we'll come back at 9:15.
Sure. Yeah.
Okay.
Just, you can stop off the door or something. Okay. Hey, just take the survey or take the survey.
Okay.
Yeah.
Thank you.
Yeah, no worries. Yeah. Ooh. Right. By the way, in your notes, go back to step 3 and put f first prime. Just single prime. The first prime. Just the first derivative. If you need to make a note, say first derivatives. Intuitively, that's conceptually easier to understand, but if you want to do it logistically, you can do it the shortcut way, like I told you, okay? You can take the second derivative and just see if it's positive or negative. It's up to you, whatever makes sense to you.
Obviously. Forgot if you're doing second derivatives so I can do them. Remedies, and then I didn't do it twice and I only did it once. So it's really
Oh, shouldn't have said that. Oops, sorry. I thought I was frozen. Sorry. That's embarrassing. I just been embarrassing myself all day. It's bad. Be very careful. I see some of you guys might have made a mistake. I got -7/4 for the inflection point. Because you guys should have had y double prime is 24x plus 42. When you set that equal to 0, you subtract 42 from both sides. Okay. Your inflection point is -7/4. In case you got +7/4. Don't worry, it's definitely a lot more than one person you got it wrong. Okay. All right. Well. Yes. Sorry. Yeah, I'll show you. Yeah, it's a lot more simple than it looks, or what it sounds like. It implies that you have to do, but it's actually not that bad. Oh dear, this is. You guys want to see the answer? Yeah. Yes. Okay. All right. Here's what I got. I'm gonna unfreeze it. Sorry, I didn't necessarily show the work. In life, sometimes the teacher can get kind of lazy, but this is what I got. I got concave down, concave up. And that does confirm that it is a point of inflection. How do I? So last time I didn't give you the interval. The interval is this. It's simply x must be lower than -7/4, and then you would just say that is the interval for concavity down. That's it. You just list that and just say concavity down for me. That's it. Okay. Not looking for anything too formal. That gets the job done. For this, you would just say for concavity up, x is greater than -7/4. That's it. So that's the way I want you to phrase your answer. Okay. No fancy notation. I do apologize. That's on me because I just thought this was a quick and easy way to say your answers. So you would say concave down, and concave up, and then one more thing. Come on, get out of here. Ugh. Here's what the graph looks like at about 7.4. That's -1.75. You guys can see right there from here. If I freeze that really quick. Okay, sorry. This is concave down. This is concave up. Okay, as we suspected. Also, there are instances where if you have a situation where like let's say the slopes are increasing and increasing, you do not have a point of inflection. Okay, let me repeat that one more time. If you find out your slopes are either decreasing and decreasing, you may have a situation where you don't have a point of inflection. A point of inflection is where concavity changes. There are instances, again, I will say it one more time, there are instances where your slopes may be decreasing on the left-hand side of the point and then decreasing on the right hand. That does happen. That means you don't have a point of inflection. Okay? Point of inflection is where it does change. Keep that in mind. I'll show you an example. Actually, I can't. Next week's the test. I probably won't be here too as well. So it's going to be interesting to your test next week. Okay? I'm going to post up another video, maybe continue it. Otherwise, guys, I'm sorry. Throw your cheers. Please go now. Thank you guys so much for coming to class. You guys are awesome. Thank you for being patient with me too. Someone hit the lights too. If you may, please, whoever. Thank you so much. Thank you.